Hi everyone. My name is Eric, and today I'm going to be going over day 3 segment trees, which is like day 2 of range queries, the advanced lecture. So, before we go into the lecture, I want to remind everyone that you need to solve 10 problems in total on the VJudge in order to pass this class. So, that's about like one problem per lecture. Um, and yeah, so if you just do a few problems every time, you're on you're set to get credit for this course. So today we're gonna be going over how to implement segment trees in Python, as well as like updating segment trees, sparse segment trees, and if we have time at the end, we'll go over lazy propagation. So let's review. So yesterday we went over prefix sum. So we would compute the sum of every prefix, and then we would use the difference of two prefixes to find the sum of a range. For example, in this array, we want the range from 2 to 5. So we get the prefix sum of all the elements up to the 5, which is 28. And then we subtract the prefix sum of all the elements on the left of the 2, which is 9. So we get 28 minus 9 equals 19 for a very efficient way to compute a range sum. But this relies on the fact that addition is invertible by subtraction. What if there's an operation that is not invertible? For example, the maximum operation. So the problem is, given an array of n non-negative integers, we want to process Q queries of the form given an interval from left to right, output the maximum value of the AL plus 1 to like AR. So the maximum value inside that range instead of the sum of all the values. So if we try to use a prefix max array instead of prefix sum array, we could create a prefix maximum array, but then there's no like invertible invert option. So like we do have that the maximum of all the elements from this beginning to this 5 on the right side is 8, but we don't have any way to take out all the elements to the left of like the left side of the query range. So the naive approach to do this range maximum operation is to just like go through every element and get the maximum of all the elements in the range manually. So the time complexity of this is linear time, O of n, because to compute the maximum element of a range of size 10, it takes 10 iterations. Is there a way to speed this up? One approach is to merge every pair of indices. So like this 3 and the 8, it becomes the maximum of the 3 and the 8 becomes 8, the maximum of the 2 and the 1 becomes 2, 6 and the 3 becomes 6, and so on. So now, instead of like going through every element, we could go through pairs of elements at a time, which speeds up the computation by a factor of 2. It's still linear time, but constant factor optimization does help speed up the program. But like, take a look at the array of like that we just computed, the array of the blocks of size 2. We're doing a really big range query on that array too. So we might be able to optimize it with the same optimization again. For each pair of arrays in the second array, we could create a third array that computes the maximum element of like each pair of the second array. And this speeds up the time complexity by a factor of 2 again. And we could do this, we could continue doing this on and on until we are left with only one segment. Here we would have log n layers because every subsequent array that we compute has like half the number of elements of the previous array. So this data structure could compute like range maximum pretty quickly, but it's also kind of hard to keep track of because there's just so many segments. And a more simplified approach to this, to creating this, a more simplified approach to creating this data structure is to start with like the one segment on the top here and recursively divide the segment into smaller segments until you're left with like the bottom segments of size 1. So this recursive data structure is known as a segment tree because it takes the form of like a binary tree, and it has like, and every node is a segment of the array or represents a segment of the array. And so let's go into how to implement a segment tree. So every segment tree is defined on a contiguous segment of the array from left to right. So let's store these two, like, let's store the left and the right as segment left and segment right. And next, every segment has two children, the left segment and the right segment. So we just like find the midpoint by taking the average of the left and right. And then we would define another segment tree on the left child and the right child. However, if the segment is size 1, it represents a single element in the array and it can't be split into smaller segments. So we just like return here so it doesn't create the children. And in the previous example, every segment also stored like the maximum element in the segment as like a pre-computation element. So let's do that here. So if the segment is size 1, it represents an element of the array. So we just assign it to that element. And otherwise, the maximum element in a segment is like the maximum element of the left segment or the maximum element of the right segment. You just like take the max of those two elements. Does anyone have any questions so far?
So for this use, we're replacing calculating the average with the max instead.
Last time we did calculating the sum, right?
No, I'm talking about the first implementation of the tree you were mentioning.
Oh, the previous one, like this one?
No, I think like
You're not replaced. No, the average is like the midpoint of the two, of like the segment.
But here we're doing the max.
No, you're still calculating the midpoint in order to compute the two children. But wait, here the midpoint isn't something that you're storing. It's like something you use. So you could split the root into a left child segment and a right child segment. Because the whole data structure thing is that we're taking a segment that represents the entire array and splitting it into two smaller segments. Instead of like starting from small segments and merging up, we're like starting from a big segment and splitting it into two smaller segments downwards, because that's easier to keep track of. So here we're just like taking a root segment and splitting it into a left child and a right child. So you have a midpoint, which I guess you could see this as an average, but you could also just see that as like a dividing point that you're dividing the root segment into. And this is just from the previous example because we want like the range maximum. We're like computing the maximum element in the segment. Does that make sense?
Okay, I think I see. The midpoint's kind of like regarding the indices.
Yeah, it's regarding the indices that you're splitting the segment into. So how do we actually calculate the range query operation? Let's define the query operation as like the maximum element in the intersection of the query range and the segment. The reason why it's the intersection and not just the query range is because the query range might lie like outside of the segment, where like it might intersect partially with the segment, because not all segments cover the entire array. And so there's three cases. The first case is the segment falls entirely within like the query range. Then the intersection of the query and the segment is just the segment. So you could just straight up return the maximum value at the segment that we pre-computed. The second case is when the segment lies completely outside of the query range. So here, the query doesn't make any sense and we want to return basically nothing. Or in this case, we could return 0 because 0 is smaller than any array element. And when we do the maximum operation on 0 and something else, the 0 basically disappears. So it represents nothing. And the third case, well, the segment partially intersects with this current range. We could just like ask the left child and the right child for, you could just query the left child and the right child and take the maximum of the two queries, because the left child and the right child, they sum up to this entire range. And so you're just like asking them to compute it for you. So implementation specifics. The first case, if the segment lies entirely inside the query range, that means the left side of the query is to the left of the left side of the segment, and the right side of the query is to the right of the right side of this segment. So that's what this if statement is checking right here. And you just return the max element that you pre-computed in the initialization. The second case is when the query is disjoint from the segment. You could check this by seeing if the left side of the segment is to the right of the query, or if the right side of the segment is to the left of the query. And you just return like 0, or in this case, -1 because -1 is like smaller than any element that's going to be in the array. And it would just vanish. And the third case is that you query your children. And the reason why you could just query your children, you could like prove that it's correct by induction, because if you query your children and your children is like size 1, it just represents one element in the array. And it's correct because it just returns the element if the segment lies within the query, and it returns nothing if the segment lies outside of the query. And otherwise, if you assume your left child and right child have correct query operations, then just merging their query operations would also be correct, because because the two children, they cover the entire range that the segment is supposed to cover. And does anyone have questions? Wait, let's go over an example first. So let's query this range from L to R, from this 1 to this 4. And so we start at the root node. The range like partially intersects the root node. So then it calls the query operation on the left child and right child. It like propagates the work to its children. And then we go to the left child. Let's take a look at the left child first. The left child, it also partially intersects this range. So it queries its children again. But then this 8 segment, it's like completely disjoint from the range. So it returns like 0. And this 9 segment's completely within the range. So it returns its max element, which is 9. And then you merge the 0 and the 9, and you get 9 because this 0 is supposed to vanish. And then on the right side, this 14 range queries its 2 children. This 14 lies completely inside the range, so it just returns 14. This 13 has to query its 2 children again. And then again, the 6 element lies completely within the range, but the 13 is just joint from the range, so the 13 returns 0. And then you merge, and you merge, and you merge, and you get that the maximum element in this range is 14. So does anyone have any questions about queries so far?
Just to make sure, you compute the basically all those rows in the beginning, and then you query them afterwards, depending on the query that you get, right?
Oh yeah, here in the initializing function, you're already computing all the max elements in the range over here, and then later you get query operations where you like returns. Okay, so what's the time complexity of the query operation? Let's take a look at something more simple first. Let's say the query is a prefix query operation. So the left side of the query is the left side of the segment or lies to the left of the left side of the segment. So it queries like a range that's like on the left side of the segment. So let the time complexity to query a segment of size n be f of n. Base case, f of 1 if the segment is size 1, the time complexity is O of 1 because it just returns its element or it returns nothing. And otherwise, there's two cases. The first case is when the query is like completely covering the left child and partially covering the right child. So because the left child is completely covered by the query, its time complexity is constant time because it just returns its max element that it pre-computed. And the right child, the time complexity is f of n over 2 because the right child has like size of n over 2. It's like half the segment size. So the second case is when the query partially covers the left child and doesn't cover the right child. So here, the left child time complexity is f of n over 2 because that's just the query time complexity we defined earlier. And the right child time complexity is constant this time because it is disjoint from the query range. So it just returns nothing or like 0. And here, in both cases, the time complexity of f of n is f of n over 2 plus a constant factor. So if we like expand out f of n over 2 to be f of n over 4, f of n over 8, like you keep dividing by 2 until you reach something that's like 1 or less than 1. Well, then then you get this constant factor, but you get it log of n times because you're dividing n in half every time, just like during binary search. So the time complexity is log of n. Does this make sense? Does anyone have any questions? Okay. So the same proof for prefix maximum queries could also be used for suffix maximum queries. And then let's check general queries this time. Well, if a query lies, like if the query intersects the middle of the segment, so the query has some part in the left child and some part in the right child, then what the segment is calling is actually a suffix maximum query on the left child and a prefix maximum query on the right child. So then the time complexity is just log n plus log n, which is still log of n. And if the query only lies in one of the children, then once again, f of n is basically f of n over 2 because the children that lies, the child that's disjoint from the query has a constant time complexity where it just returns 0. And the child that has the query has time complexity f of n over 2. So once again, f of n equals f of n over 2 plus a constant factor. So f of n is log n again. Does this make sense? Does anyone have any questions right now? Yeah, because the first like comparison, it checks if the query is inside of the range. If the query is like completely disjoint from the range, it just returns 0. So let's make this problem a little harder. Let's add an operation where given P and V, you set this element at P to V. So this is actually something that segment trees excel at that prefix sums can't really do, because when you update an element for the prefix sums, you basically have to recompute the entire prefix sum array. But for the segment tree, you actually only update a certain number of elements. For example, here, let's update this 14 to 10. You would update this segment of size 1, which represents the element 14, and then you would represent its parent, and then the parent's parent, and so on. So you would actually only update one element every layer of the segment tree. And since there's only like log layers, because in every layer the number of nodes decreases by a factor of 2, then this would be like log of n. We'll prove this even, we'll like continue this proof later, but let's see how you would implement it. So we're defining an update of the index P and a value V. We're gonna assume that the index P lies within the segment, because there's no point in updating the segment if the index P lies outside of the segment. So first of all, we check which child this index lies in. So here we're saying if P less than equal to self.leftchild.segment right, then you update the left child. And this is because self.leftchild.segment right was previously computed to be the middle of this segment, and you're just asking if the index lies left of the middle of the segment, or if the index lies to the right of the middle of the segment. So if the index lies to the left of the middle of the segment, you would update the left child, because that's the segment where the index lies in. And otherwise, you update the right child. And then you would update this current segment again, because the left child and the right child might have been changed. So you have to recompute the max element in this segment. This code is identical to the initialization code, where you're like merging the two segments and getting the maximum of both segments. And then lastly, if the segment has size 1, so if the left side of the segment equals the right side of the segment, this segment represents like the individual index in one of the arrays. So you just set the max element to the updated value. And does this make sense? Does anyone have any questions? Okay. And moving on, what's the time complexity? Since you're only updating a single child, f of, like, let's assume the time complexity of updating a segment of length n is f of n again. Since you're only updating a single child, f of n would be f of n over 2, and then plus some constant factor, because you're doing some updating to this current vertex 2. And then from before, this equation leads to like a time complexity of log n. And so here we're creating a seg tree over like range maximum, but a segment tree could also be created on other operations, such as the sum operation, maybe multiplication, or the only requirement is the function has to be associative, because the segment tree doesn't compute like the merging operation in order. And this is better than prefix sum array, because in a prefix sum array, you would need a way to invert the operation. And also the prefix sum array doesn't support efficient updates like the segment tree does. And next we have a little bit of live coding. So in this problem, you're given n and m. N is the number of elements in the array. M is the number of operations to perform. And then after that, we're given like all the elements inside of the array that's its initially is. And then we're given one of two operations: the modification operation, where we set an index to a new number, and the query operation where we query a range from left to right. So let's take in the input first. Here we have n q equals map int input dot split, and then we have array is array of size n for I in range n. Let's input into the array. The element at index I is int input. And then after that, we have a couple of queries here. So for query in range Q, what we're doing is we're reading in 3 elements. The first one's a string, and the other 2 are integers. So it's input.split. Since the other 2 are integers, let's set them to integers. And okay, now we kind of need a segment tree data structure to actually solve this problem. So let's define a segment tree. The first thing to do when implementing a segment tree is the initialization function. We have to initialize it over a range and also give it an array to initialize with. So let's store the left and the right. And then if L equals R, if the segment is size 1, it represents the specific index in the array. So we just set self dot. Here we're doing range minimum, so min element is just array L. And then let's return here. Otherwise, we have mid equals L plus R over integer division over 2. And then we create the 2 subsegments, the left child and the right child. Oh, I forgot to also pass down the array because it needs the array for initialization. So now that we have the left child and the right child, we need the minimum element in the current segment. So that's just the minimum of the minimum value in the left segment and the minimum element in the right segment. So that would be self.left child.min lm or self.right child.min lm. And that should be it for the initialization function. So now we could define the segment tree. So let's call it tree equals segment tree, and it's defined on 0 to n minus 1 because Python is 0 indexed, and these are all the indices in the array. And then let's pass in the array. Oops, this has to be after the input. And then next, we need to define the query operation. So define query self LR. So the first case is if the segment lies within query range. So if self.segment, sorry, if L less than equals self.segment left and self.segment right less than equal to R. So L segment left, segment right, R is like the order of like the ranges. And this, if this is true, this means the segment lies completely within the query range. So what we do is we just return the minimum element in this segment. And then Feel free to interrupt me by asking any questions at any point in time, by the way. If this segment lies completely like outside of the range, then we want to return. This time we want to return a really big value because that is the value that would vanish in a minimum operation. So if self.segment left is to the right of R, or self.segment right is to the left of L, I think this is when the two segment is disjoint from query range, then we just return. What you could do is in Python is you could just return infinity. And otherwise, we return the minimum of self.leftChild.query the range, or self.rightChild.query the range. And lastly, we have the update operation, which we update some index with some value. Let's first assert that the index is within the range. So self.segment left is less than or equal to index less than or equal to self.segment right. Python has this really weird quirk where you could chain less than or equal to signs, I think, but I don't like that. So let's do this. Next, if self.segment left equals self.segment right, this means this range is size 1. So what you do is you just set the min lm to be the value. If self, otherwise we check which range the index lies in. If index is on the left side, that means it's less than or equal to the right side of the left segment. Then we update the left child. So we pass in the index and the value again. Otherwise, we update the right child. And then we need to update min lm because one of the children are updated. So we need to make sure this min element is up to date. And what we could do is we could actually copy and paste the code from here because it's the exact same code, the merging code from the initialization. You just set the minimum element to either the left child's minimum element or the right child's minimum element. And I think this should work. So we check if A equals that's like the first operation where you set the index 4 to this number. So you just set tree.update B, you set the index B to the value C. Otherwise, print out the range. Otherwise, it's a query operation for a certain range on this segment tree. So we print tree.query B, C. And let's see if this works. For the input, we could copy this. And then we run the code. Oh, and there's some errors. Let me check. So here it says segment tree has no attribute left child. Oh yeah, because if the segment is size 1, it has no children, so we could just return at this point. And now it's giving us some output, and I think this is the correct answer, so we could submit this code. So we're submitting to PyPy because apparently it's faster than Python. And let's see. The judging of doom. Oh, it's accepted. Nice. So does anyone have any questions on the live coding? Okay. Moving on. Let's talk about sparse segment trees. So let's update this problem in a kind of strange way. So instead of an array of length n less than like 2 times 10 to the 5, we're making the array really big. We're making the size of the array 1 billion. So because there's no way you could input 1 billion integers without like time limit exceeding, without taking too slow, we're gonna initialize every element in this array to be 0. And then we're gonna slowly modify the array with with a few like queries where we set some element in this array to some value. So we want to, first of all, let's modify our segment tree to like not be initialized with some array anymore, because the initial array is all zeros now. So we could just set max lm to 0 and delete anything involving like setting the max element. But there's a few problems with this. Like even after we modify the segment tree in this way, it takes way too much memory, because every like individual array element has its own segment defined on the segment tree of the, like every segment tree. Eventually, like one of the children will be a segment of size 1, and you would have a segment of size 1 for every element in this array. So you would have at least 1 billion nodes. This is way too much memory. But a certain insight is that before a node is accessed, whether its children exist or not doesn't matter, because its children are just both initialized to be like all zeros. So why not dynamically allocate like the memory of each children when you access a node in like a query or update operation? So in this case, let's like refrain from allocating the children during the initialization operation, because when you initialize it, the segment's not accessed yet, so you don't need children when it's so we just set the children to be none. And then let's create an access function. Let's say this access function is called whenever the segment tree, the current segment, is accessed. Then when it's called, you just create the left and right child. Some corner cases are if this current segment is a segment of size 1, you're not going to create any children, so you just return. Or if you already created the children, there's no point in recreating them, so you also return in that case. And we just input this access function whenever we access this node. So we put it in query and we put it in update. We put it at the very start because we want to allocate the children in case the query or update operations use the children to do stuff. And yeah, that's about it. So what happens is, instead of allocating 10 to the 9 nodes every time you initialize the segment tree, you only allocate the children whenever you do a query or update operation. And since the time complexity of query and update are like log of n, then the self.access function is only called like log of n times. And so you're only allocating around log of n memory. Okay. Does anyone have any questions? Eric, is there time for lazy or? Okay, let's present on lazy segment trees. So let's make this problem a bit harder. Instead of setting a single element to be, we're setting a range of elements to be a range. So we now have both a range set and range query operations. So naive range set would be n log n because you're updating every element one at a time. But what if there's a way to like update entire segments? So lazy propagation, the way you implement lazy propagation, like the way you implement the range set operation is similar to queries, where you update like entire segments. So in the query function, it stops when you reach an entire segment that's inside the query range because you just return the value of that segment. In this update operation, you stop when you update a segment that's entirely within a range because you just update that entire segment. And usually that segment would have to update its children in order for this to work. But the key insight is similar to like sparse segment trees, where you only have to update your children when you access a node, because if you don't access a node, it doesn't matter if your children are updated or not. Like if they're outdated or wrong, it doesn't matter because you're not going to access them. So this is what is called lazy propagation, because you only propagate the updates last minute. So you're being lazy when you do so. And to implement this range update mirrors the code of range queries. So you have the two cases where the segment is inside the range, or this case where the segment is disjoint from the range. And if neither of the cases happen, then there's something wrong with this code, because you have to return after updating here so that it doesn't update the left and right child. But after that, if neither of these cases happen, you just update each children individually, and then you update the current max element to be the max of the left child's max element, or this should be min element. Anyways, you note that we also have self.access at the very beginning, because we're accessing the node when we're updating it. So we want to like do the stuff where like we want to create the children of the node. And let's define the lazy update, because here we're calling self.lazy update without actually defining it. So when we define a lazy update, we actually update this range. So what this update is doing is we're setting every element in this range to v. So the maximum element in this range would also be v. So you could just set max element to v. And the dot lazy update, we're defining a dot lazy update. No, we're defining a has lazy update variable where it's true if this current range has a lazy update that it needs to propagate. And we're also defining a lazy update variable where it's the update you need to propagate. So you're setting that to v. And we're modifying the access function because when we access a node, we should propagate the updates downwards. So what happens is at the very top of the access function, actually no, not at the very top, but okay. At the very top of the access function, you check if you have a lazy update, and if you do have a lazy update, then you update the left and the right child, and then you set has lazy update to false. This code is currently slightly incorrect because you also need to check if the left child and right child exist first. So I think this should come after the code where we define the left and right child and check if this segment is size 1. But other than that, this is how lazy propagation works. Does anyone have any questions?
Did you ever have multiple lazy updates?
So if you have multiple lazy updates stored, the latest update overrides the previous one. So what happens is you don't have to there's certain functions where if this lazy function is a sum function instead of a set instead of the set function, then what would happen is we add to the lazy update. So this would be lazy update equals self.lazy update plus v, because you're merging the two update functions into one update function for efficiency.
So if they like apply to different
Wait, what do you mean by apply to different ranges?
like the update applies to like a certain left and right. If you're
When you're doing the lazy update, the update would apply to the entire range.
yeah, so then if you have two of them, but they're like in different parts of the array, like different ranges of the array.
You're not updating the segments until the segment lies completely inside the query range. It's similar to like queries where you're not returning the elements until the query lies completely within the range.
What are the situations where max element, the self.max element and self.lazy update would be different? Is there
Well, for some, it would be different. Like, let's say you have range sum instead of range max. So it's a bit more complicated when you have range sum, because like instead of max elem, you would probably have a variable called sum of the elements, right? Sum elements. Sum elements would be if you have a range set operation, it would just be v times the length of the segment. Because, or if you have a range add operation instead of a range set operation, you would have to, it would have to be the range sum of the left side plus the range sum of the right side plus v times the length of the segment, because you're adding v to every element in the left and the right side, every element in the segment. Does anyone else have any questions? If not, that's the end of the lecture. Here's the attendance form, and you could reference the live coding segment tree for any of the p sets on this link. Thank you all for listening. Yeah.
we'll start problem solving